His research interests include geometry, dynamics, and discrete groups, and today he's going to be talking to you about triangular billiards.
Well then, thanks for inviting me to this. So I want to talk about a pretty simple problem, and I'll first talk about just billiards in a polygon. So the way this is set up is that you have a some kind of polygon, which you should imagine is a billiard table or a pool table, and then you're interested in what happens if you play pool with an infinitely small ball. There's no friction, and it never goes in the pockets. So you start geometrically. What you do is you just start drawing a line, and then when you come to an edge, you bounce out so that the angle that you bounce in is the same as the angle you bounce out. So another way to say it is if you just draw a little circle around that, you see a perfect K. And if you thought of this as a beam of light, then it would just be like it was bouncing off a mirror. So you just can follow this around. And it might turn out that the thing actually comes back and retraces exactly what it did before. If it did that, it would be called a periodic billiard trajectory, or maybe a closed billiard trajectory. It goes by a number of names. And one of the most basic questions you could ask about billiards is, can you put the balls, can you start somewhere and in some direction so that you actually do get a periodic billiard trajectory? So just in terms of the game, can you hit it somewhere so that it actually comes back and just retraces its initial path? And, you might ask why you would be interested in this question, and one answer to this question I would say is that you could say that billiards was kind of a prototypical example of what you would call a dynamical system, where you have some kind of basic process, in this case kind of moving along a straight line until you come to a wall and then bouncing off it. But in general, you might have some kind of basic process that just repeats over and over again according to some basic rules. For example, the evolution of the planets in our solar system, how they sort of go around each other and what happens. And you might be interested in periodic orbits, or these kinds of periodic trajectories, because they're kind of the simplest sorts of things that would happen. Actually, if you lived on the Earth, you would be really interested. You wouldn't want to sort of have the Earth spiral around into the sun. You would want it to sort of just, every year basically do the same thing, so you could go on surviving. So, and billiards is again, it's kind of a prototypical example. I thought I would show you one example where, if you look at billiards in a right triangle, it's related to particles bouncing around on a line. So I wanted to at least show you one example where it does look a little bit like physics. So, if you had say a straight line, and maybe you had a barrier at 0 and another barrier at 1, and you had two particles in here, you could call one of them the x particle, and the other one the y particle, and you could imagine that they were sort of allowed to bounce around, and they could bounce into each other and then they'd collide according to an inelastic collision, or the y particle could hit the 1 and the x particle could hit the 0. These guys would just sort of bounce around. You might ask, like, what happens? How do you describe kind of what's happening to these particles? And one way you could do this is you could plot the point x, y in a plane. I think I already blew this. So this point x, y, x can be bigger than 0, y can be less than 1, and then y is greater than x. So the range of possible places for this one point here, this xy point, represents these 2 points here. And as they move around, the xy point kind of travels around, and it turns out that, like, when it hits here, this corresponds to these 2 points colliding. And then as it goes off, it kind of corresponds to them moving. And it turns out if they have the same mass, and you just set them going at some initial position and watch what happens, you are just kind of watching billiards in a right triangle. In fact, in an isosceles right triangle. So if you wanted to sort of study, like, do these things ever come back to their initial positions, you'd be asking about periodic billiard paths on this particular triangular-shaped billiard table. If you had more particles, like 3, you could plot all 3 of the coordinates and you get some kind of tetrahedron in space. And you would be talking about billiard ball kind of bouncing around inside the tetrahedron. If you had more particles, you'd have a higher dimensional kind of shape. So kind of this basic example, the billiards in a triangle models some kind of physical behavior of a system of particles on the line. But I don't really want to talk too much about the physics of it, partly because you now have heard about 99% of what I know. But I want to talk about just the geometric problem of trying to understand billiards in polygons, and especially in triangles. So the most basic kind of question you can ask is, does every triangle have a periodic billiard trajectory? In other words, if I give you a certain triangular-shaped billiard table, is there some place where you can start the ball rolling so that the thing comes back and retraces its steps? And I kind of got interested in this problem a couple of years ago. The thing that attracted me to it was that it has actually been an unsolved problem for about 200 years. People still don't know the answer to this question. It's kind of surprising in a way. You'd think that you could sit down and just find an answer in an hour or so. So I thought I would tell you kind of briefly what is known about this problem, and then I would talk about this computer program that I wrote with another guy to sort of explore this problem and the kinds of things that come out of the computer program. So, so let me tell you 3 cases where this is known. So one case, so an acute triangle is one where all the angles are less than 90 degrees, and a rational triangle is one where all the angles are rational multiples of pi, like 3 pi over 7 or 2 pi over 9. So I want to just quickly convince you that every acute triangle has a periodic billiard path. What you do is you imagine you have a rubber band that's kind of constrained to touch these 3 points, but otherwise it kind of wants to assume the minimum length it can possibly assume. And if you just let the rubber band go until it assumes its minimum length, that actually turns out to be the trace of a periodic billiard path. So here's a little mathematical proof that that works. So I've got this triangle, and amongst all possible blue triangles that fit inside this big one, it's the one of shortest length. What do I need to show that it's a periodic billiard path? I need to show that if I look at a corner, it makes a perfect K. That's what I need to show, and then I'm done showing that it's a periodic billiard path. So what I can do is I can pick 2 points, and what do I know? I know that this thing is the shortest path from here to here. So I can take this point and imagine that this is like a mirror, and I can look at this point in the mirror. So I know in the mirror the shortest path that joins them has got to be just a straight line segment. But then whatever path I have joining them here, to get the shortest path here, I just would take this one and I would reflect it back in the mirror. So in other words, the fact that this is the shortest path joining these 2 points means I got that path from taking the straight line segment and then just reflecting the second half of it. And when I do that, that's exactly the condition of light bouncing off a mirror. So the shortest path has this kind of property. It's like light bouncing off a mirror, and that's the argument. If you try to do this for a triangle that's not acute, like if you have a really long, thin triangle and you try to find the shortest, if I put a rubber band on this thing, what'll happen is it'll just kind of shrink down to nothing. The acute triangles have the property that you really do get an actual shape. So that's why right triangles, acute triangles have these things. For right triangles, some of you may have experimented with mirrors in your bathroom. If you hold two mirrors at right angles and you look into it, you'll see your face perfectly reflected. That's sort of a basic fact about mirrors. Another way to say it is if you shoot a gun into the corner of the room, then it'll come back and hit you in the face. It's sort of a completely equivalent statement. So the idea is if you want to produce a periodic billiard trajectory on a right triangle, what you should do is you should start out perpendicular to the long side, the hypotenuse, and then you go up, and when you go over, you come out exactly the same way. So you come straight back down, and then you just bounce back up again, over and down. And then, so actually this thing, it looks like, I mean, after it hits 3 sides, it doesn't come back, but after it does another 3, after 6 sides, it's completely come back. So this is another example of this works for any right triangle. So this is an argument that every right triangle has a periodic billiard path. For the rational case, I thought I'll kind of explain why a rational, I'll give you kind of a heuristic or rough argument why you would expect a rational triangle or polygon to have a periodic billiard path. So the idea is, let's say this is kind of a strange, you're probably thinking this is a strange looking triangle, but actually this argument works for any polygon whose angles are just rational multiples of pi times a fraction. So the idea is you start out perpendicular to a side, and you start bouncing around, and if you ever come back perpendicular to the same side, you win. You've got your periodic trajectory because then it just endlessly retraces what it does and it comes back, just like the thing I just shown you for the right triangles. So you kind of let this thing go and you watch it bounce around, and then the idea is, well, it kind of bounces all over the place. So it's bound to come back sort of around here often. It'll bounce around and it comes back, it goes out again, it comes back, it keeps coming back. And the fact that all these angles are, I mean, it might come back and it might be rotated. But the fact that all the angles are rational multiples of pi means it can be only rotated in one of finitely many positions. For instance, if all the angles were like something pi over 9, then it would only be in basically 9 possible positions, or maybe 18 possible positions. So you should just wait long enough, and eventually it's going to come back. I mean, the way it comes back is something like a coin flip. You know, maybe an 18-sided coin flip. So it just keeps bouncing around and coming back, and you just wait, and long enough the thing's eventually going to come back the right way, and then you're finished. That argument leaves some room for doubt that it really works. But actually it does, it actually works. But I'll leave it at that. But that's sort of the heuristic reason why you would expect a lot of periodic trajectories on billiard paths with rational angles, because the path kind of goes all over the place, and frequently it's rotated exactly the way it was when it started. Yeah.
Well, what did you do when it hit the corner?
You get a you score a point. You just don't consider those. They're just sort of left out of the.
It's like those paths that went around the cylinder.
Yeah. They're just. The fact is, the chances of actually doing it, you would say that it has zero. You have zero chance of actually doing it, or zero probability. So you just kind of throw those out. I'm sort of leaving out a big story. For rational polygons, it's known that just to tell you some things that are known, like if you count the number of, say, the number of billiard paths length of, you could say not only is there one, but how many are there? So you could say, like, how many different billiard paths are there of length less than n? And for rational polygons, it's known that it's something like, and what this proportionality constant, what this means is that it's like it's between n squared over one constant and n squared times that constant. So like it's between 2n squared and n squared over 2. So this is a theorem of Halley-Mazur's. So actually, they can sort of count the number of billiard paths. So I thought maybe just briefly I would give you some explanation of why this was true in one case where you can see it. So one case that you can understand is if you're on a square billiard table. So think of it as a billiard table where the sides have length 1. Then, say you start in the middle and you start bouncing around, rather than actually bouncing off the, reflecting off the side of the billiard path, you could reflect the table around the billiard path. In other words, if this was really a mirror, then this light ray, you can think of it actually as just going straight. And so, as you're bouncing around in here, if you just sort of always straighten this thing out according to which side you hit, what you get is some kind of path of billiard tables. And if you want to reconstruct the original path, you just kind of fold this thing up, like one of those Jacob's ladder puzzles. And what does it mean for the thing to close up? It means that eventually it hits another point, another grid point, a point in the plane with integer coordinates. So if you're really counting, say, the number of periodic billiard trajectories that start here and have length less than n, you're counting the number of grid points inside a disk of radius n. And there's about like pi times n squared of those grid points. So that's saying that the number of periodic billiard paths of length less than n is it's like a constant times n squared. So that's sort of some kind of argument. I mean, the argument for a more complicated kind of rational, well, it's a more complicated argument, but I mean, this is some kind of rough idea of what's going on. So, so I wanted to, anyway, a lot is known about these rational polygons, but nothing is known. The case I left out, just for triangles, was the case where it's an obtuse triangle and the angles are irrational. So that's a case where basically nothing has been known. And so I wrote this computer program called McBilliards. And at some point, this guy named Pat Hooper. So I wrote some kind of initial version of this, and Pat souped it up a lot. Most of what you like about the program will use Pat. But anyway, he's a grad student at Yale, just graduated. So I'm going to show you, in about 2 minutes, I'm going to cut to the chase and show you what McBilliards does. But before I show you what it does, I need to tell you 3 things so you can understand what I'm going to do on the computer. So the first thing is pretty simple. Maybe I'll actually just cut to the chase, show you the program. This the window up here, each point in this window represents a different triangle. So and the way this is done is that the point xy represents the triangle with angles, basically, well, x and y. It's really, yeah. So, so as I move around in this top window up here, I'm sort of getting, like, I guess I can show you this. If you look on the bottom, let me so if you look down here, you can see a bunch of triangles, different shaped triangles. I hope it's clear enough to see. Maybe I can change the color. Let's see. Yeah, that's better. So there's some triangles, and as I move around up here, the shape of the triangle changes according to where I'm clicking. So this whole square here, like when I'm on this red line, these are all right triangles. When I'm up here, these are acute triangles. And when I'm down here, these are obtuse triangles. And as I go out towards the edge, the triangle gets more and more obtuse. And you can just kind of move it around, and you can see, anyway, you can see some triangles. So that's the first thing to understand, is that this square represents kind of the set of all possible triangles you could get. The second thing I want to explain is the idea of an unfolding of a billiard path, which is what I sort of already talked about this for the case of the square. Rather than have the billiard path bounce off the triangle, I could reflect the billiard path according to reflect the triangle according to the billiard path. So I want to show you this example down at the bottom. If you look down here, maybe I'll do that. Like this billiard, if there was a billiard path, what it would be doing is it would first be bouncing off this edge, which is the second one, and then it would be bouncing off the third one, and then it would be bouncing off the first edge, then the second edge, then the third edge, and back to the first edge. Now, the fact, when you draw this thing, just to take this example, there's several things to notice about this picture. One thing is that this first edge is parallel to this last edge. And secondly, there's this white strip. And so here's a recipe for producing a periodic billiard trajectory. What you do is you just take any line that goes inside this strip and parallel to it, and then you draw the line, and then you just fold it back up into this first triangle. And that produces a periodic billiard path. And you could ask, which one does it give you? Well, in the very beginning, I was telling you that there was this one that went around for the acute triangles. So if you just do the one for the acute triangles, but you go around twice, this is the one you get. So the fact that wherever you click, you see the parallel sides, and you also see this kind of white strip. That's an indication that this periodic billiard path works for all those triangles. Okay, so anyway, that's the second thing I wanted to explain to you, which is just this unfolding of a billiard path. The last thing I want to explain is what I would call kind of the combinatorics of a billiard path. So if you have a billiard path in a triangle, you can keep track of the sides it hits. Like first it hits side 1, and then side 2, and then side 3, and then maybe side 2, etc. And this will give you some kind of string of digits. And you can take that string of digits, and you can actually make a kind of a picture out of it. And what you do is, now I have to draw on the board one last time. I'll tell you the recipe. You take this is supposed to be the hexagonal grid, and you take all these, say, horizontal edges and you label them by 1, and you take all the edges that are, say, pointing this way, say this way, and you label them by 2, and then you take the other ones and you label them by 3. Then, if you have some particular string of digits, say 1, 2, 3, 1, 2, 3, then you can create a path in this grid by just following it around. Like first I would take the 1 edge, then I would take the 2 edge, then the 3 edge, then the 1 edge, the 2 edge, and then the 3 edge. So if I did 1, 2, 3, 1, 2, 3, I would actually trace out a hexagon. So rather than show you just long strings of digits, what McBilliards shows you is it shows you these kinds of paths. So what McBilliards will do is you can give it a triangle and also some length cutoff that you're interested in, and it will find all the different types, all the different strings of digits which describe periodic billiard paths. It does a kind of a complete search. And if I have time, I'll talk a little bit about how it's done. But for now, I'll just sort of show you how it works, what you do. I should say also that this is actually on my website. You can play McBilliards right from a browser. Anyway, you just push the seek button. Here the length cutoff is 50. And then it finds these two guys. One of them has length 14, the other one has length 34. So the length 14 one, well, anyway, it's down a couple, then what can you do? You can select one of them. So now I've selected the one of length 14, and this is the picture of the 14 triangles. This triangle corresponds to this point, and the sequence of edges you use corresponds to the sequence of digits in the in the description of the periodic billiard path. And again, the first and last sides are parallel, and also there's this corridor that goes through the thing. So this is sort of a kind of a visual check or a visual proof that McBilliards was successful in actually finding a periodic billiard path. If you click the one of length 34, it's a little longer, but it's basically well, there it is. And again, you can see that the corridor, well, it's so blurry you probably can't see, but this is really a thin strip where you can see it. If you take any straight line through here, you go all the way to the end, and then you just fold the thing back up, it will produce a periodic billiard path that hits 34 sides before closing up. So that's the first thing it does. It searches for periodic billiard paths. And the second thing it'll do is once you pick one, you can push plot. Let me get a better color for you. And it'll plot this periodic billiard path. You found it for one triangle, but let me convince you that it actually works for many, not just this one, but for some other ones as well. The idea is that this condition that the first and last sides are parallel, it turns out to work no matter what triangle you pick. But there's a condition. What you do is you draw this path, and as long as that path closes up, then whatever triangle you use, the first and last sides are parallel. So you don't have to worry about the first and last sides being parallel if you change the triangle. It always works. The only thing you would have to worry about is if you change the triangle too much, this strip disappears. So let me just show you how the strip could disappear. Here in this red region, as I move around, as I start going towards the edge, the strip is getting thin. And out here, even though the first and last sides are parallel, the first side being this one, and the last side being this one, there's no strip that goes through it. So what this triangular region represents is it represents all the different triangles you can pick, which have the property that when you unfold this thing, you actually get the strip. So let me just plot the other one, see what it looks like. So it's really small. So in here, let me fix the color. So any point inside this pink one, it has not only this one, but also, oops. That's past all. Anyway, so you see that the ones that there are many fewer triangles that have that longer periodic billiard pattern. Yeah.
Does it always occur in a triangle there in the top window?
Oh, here?
Yeah.
Oh, is this always a
Do you
triangle?
always get a triangular region there?
That's a good question. So let's, yeah, so actually, I can see it, but you probably can't. That actually isn't a triangle. So let's just try some other ones. Maybe you'll go over here, and I'll search. It looks like I found one of length 18, one of length 36, one of length 36, one of length 48. Let's look at the one of length 18. You plot it, so no. No, it doesn't look like it. Another question you might ask is, do you always see, is this thing a polygon itself? Maybe it's not a triangle, but is it a polygon? And the fact is, no, it's not, unfortunately. One of the things that really got me excited about this problem was that I thought these things were all polygons, but then I looked closely and I noticed that no, if this edge was a straight line, it would go through the middle of this point, and it doesn't. They kind of bow in a little bit. Another thing that McBilliards will do is, well, what do these edges mean? Let's get rid of some stuff. Like, when I come to this edge, if you look at the picture, it corresponds to the place where this vertex is the same height as this vertex. Like, what you need for the strip is that all the ones that are supposedly on the top are above all the ones that are supposedly on the bottom. So these edges correspond to places where two of these vertices actually occur at the same height. And there's some equation that describes that. And actually, McBilliards will just compute the equation. If you look at these numbers down here, well, I'll just say this briefly. The equations tend to look something like summation AI sine BIX plus CIY, where I goes from, say, 1 to n. Then, instead of writing AI sine BIX plus CIY, I just store the numbers ABC. So the first column here, you probably can't see it, it's 1, 0, 2. So it's 1 times sine 0x minus 2y, plus 1 times sine 0x plus 2y, plus 1 times sine minus 2x plus 4y, etc. Now, and these things definitely aren't the equations of a straight line. So it's not, I mean, you might ask why they look like this, and you probably remember from high school that you learned about sine functions when you were studying triangles. You know, so it's sort of, the sine function sort of, tells you things about the, ratios of lengths of sides in a triangle. And here, you're kind of measuring the relative positions of vertices in a long string of triangles. So it's sort of believable that the thing that you see is a sine function, involved. But anyway, there's a fancier explanation. Well, anyway, that's a pretty good explanation. That's about all I can really say about it. That's my intuition on it. It's because it comes from triangles. But anyway, you can compute these things exactly, even though the formulas get long. Like, I'll just take a longer one. You can also kind of manually do it by hand. You can just select a pair of vertices. Here I selected this one, and then this long string of things, which actually runs off the screen. It gives you the equation. This long string of sums of sines is 0 exactly if these 2 points have the same height. So that's the kind of thing it does. So I want to tell you a little bit about how it works, but maybe I'll give you a nice picture to look at while I'm talking. Oops. Can't see that. Yeah, so anyway, so later when I talk about how McBilliards actually plots these things, I'm going to try to explain why you see all these cracks and what it means. But anyway, it's a nice looking picture anyway. So, let's see. So, all right, the thing basically does, it does two things. Basically, it searches and it plots. So firstly, just how does it search, and then secondly, how does it plot? So, I mean, if you first think about finding, if you want to know like how many different possible strings of digits are there of length less than 50, it's like about 2 to the 50, or maybe 3 to the 50. You know, and if it's up to, maybe if you're up to length 200, you're getting to sort of close to the number of particles in the known universe or something. So the question is, how does this thing search over, you know, say 2 to the 200 possible strings of digits? So what it does is it makes a kind of a word tree. So like it starts at, you know, say 1, 2, well, maybe it starts at 1, 2, 3, 1, 3, 2, 1. The thing never hits the same side twice. So it's really a kind of a picture like this, a binary tree. And what the thing does is it's got the triangle in the background. And it's searching through this tree up to some depth. And it does what's called a depth first search with pruning. So what that means is it starts going down the tree, and if it's at some place, what it does is it unfolds the triangle according to the words it's seen, and it tries to draw a straight line in the triangle. And if it succeeds, it's happy. And it also checks that this parallel condition, that the first and last sides are parallel. And if the parallel condition doesn't work, it just moves on to the next spot and keeps going. And if it eventually can verify both the parallel condition and the fact that there's a straight line in there, it counts that as a winner. So it has these various kind of good ends to it. But every once in a while it comes to a place where when it unfolds the thing, it's too lopsided, or it's too curvy. And then it sort of employs a basic principle that if you can't fit a straight line through this thing, your chances aren't going to improve by adding more stuff. So it just, anytime it sort of unfolds this thing and sees that it's too crooked, it just cuts off all futures. This is sort of called pruning. And what this does is it makes something that looks like an exponential search, something where if you do length 50, it's like 2 to the 50, it turns it into something which is much faster, like maybe 50 cubed or something. I actually don't know how fast it is, but it's much, much faster. And so it's feasible to do searches, say, up to length about 1,000, just pretty quickly. That's how it searches. I should say that's how it did search when I wrote it. And somehow various enhancements make the thing, you know, like 1,000 times faster. The actual algorithm that it runs is really complicated. But that's sort of, that's the idea. It just does this kind of depth first search through a tree with pruning. Then for plotting, what it does is it's got some mystery region that it's trying to find. And it starts out with the biggest square, and it tries to prove that the biggest square is inside the region. And of course it's not. So it replaces the biggest square by the 4 smaller squares, and it tries to show that each one of those is in the region. And if it can't, it subdivides it again. It sort of discards the ones that you can just see obviously are really far away from the region. And so it just keeps going, and in this kind of way, it zeroes in on the region. So this picture here, you can actually pick a square, and you can plot just that square, and then down at the bottom here, maybe I won't explain how this works, but there's a record of all the calculations that the thing used to actually prove that this square is inside. So somehow all these squares, I think one novel feature about this program is that if you discount things like round-off error, all these squares come with a certificate that they provably do lie inside this region. So if you're trying to construct something like a computer-aided proof that some particular region has a particular billiard path, you can actually go through, and if you're not worried about round-off error, then you can actually get a proof that a certain region does have it. And in fact, some other component of the program, which I'm not going to show you, implements something like a way of doing arithmetic that basically arbitrary precision arithmetic, and it sort of gets rid of the round-off error. So somehow you can actually use this program to prove things. And the thing I used it to prove was that a triangle has a periodic billiard path provided all its angles are less than 100 degrees. So previously no one was able to get past 90 since 1775 or something. So now you can get up to 100 degrees. That's the result. So I thought I would just show you the picture of what it looks like. You can open up this window, and then you can let her rip. You can let her rip.
Can it make them all different colors?
So that's the strip where let me turn out the lights and do this. So there's another half to this, that somehow these are the triangles just where the angles are reordered. So you really just have to worry about everything in here. So this region, this is sort of the strip where the angles have the big angles between 90 and 100 degrees, and it's completely covered by these regions. And each one of these regions provably has a periodic billiard path in it. And if you click on one of the regions, you can see down at the bottom the periodic billiard path. You can just go through and try it. So I thought just really rapidly I'd give you a tour of this. It turns out that there's no finite list of periodic billiard paths which will solve this problem. Like for the acute triangle case, there was just one that always worked, and for the right triangle case, there was one that always worked. But actually, like here, if you come out to the edge, there's this infinite family. So the thing I want you to watch while I'm doing this is this window here. So here it looks like you see these two kind of peanuts that are stacked on top of each other. And as I start going down this family, you see 4 bumps and then 5 bumps. Oops, 6. Well, if you do them in the right order, you just count more and more bumps. There's this kind of infinite family that you see over here. Somewhere in here, maybe I'll do it on this window. There's this other infinite family, and I'll show you the words. So if you watch the same window, you can see that these things are getting longer and longer. And then actually, There's yet another infinite family over here, which looks like that, like that, like that, like that. Well, maybe that one's not so clear what's going on. Carol. There. So there are these three infinite families that you sort of have to analyze how they work, but they follow a very orderly pattern, and they cover up certain regions that you would call trouble spots. And then when you're done with the trouble spots, you're just left with sort of something like 200 regions, one for each square over here. Every time I push one of these squares, it corresponds to a different one of my 200 guys that sort of fills up the easy part. You can just kind of get a sense of their shapes by going through them. It's all completely checkable. You look at, like on this part of the window over here, this actually tells you the vertices of these polygons. They're actually, these polygons here are not they're actually smaller than the plotted tile. So what I did was I plotted the actual tile and then I picked something smaller whose vertices were easy to write down. So you can sort of completely survey the word list, and and just sort of check that everything works. So maybe the only other thing I want to say about this is just that sort of the kind of ugly details that go into the proof. I mean, one question people ask a lot about computer-aided mathematical proofs is how do you deal with something like round-off error? Like this is a problem. Like how can you actually prove an exact statement on a computer because the thing is actually kind of just making calculations and rounding off and doing all kinds of things. So I thought I would just say a word about that. I've got this formula. And it turns out that when I'm doing my plotter, it turns out that I'm only evaluating sign on numbers of the form k times 2 to the 20, where k is equal to 0 up to 2 to the 20. And so what I do is I just take this thing in advance, and I multiply it by something like 2 to the 50. And rather than compute this thing, I compute this thing. I take 2 to the 50 times sine of that, and I kind of put it inside two integers, which I could call I sub k and j sub k. So I can just replace this thing. I find one integer that's less than it and another one that's bigger than it. And then when I compute this thing out, I really compute two quantities, one using these integers and one using these. And I just get a pair of integers which does contain the actual answer. So if I'm trying to show that the actual answer is positive, for example, I could just show that both of my kind of integer sums are positive, and that'll do the trick. And fortunately, a computer programming language like Java has, it allows you to manipulate arbitrarily large integers. So anyway, the thing does lots of other things besides what I showed. But anyway, there's the program, and it's on my website. You can actually play with it.
Have you made a similar program where the billiard table is not necessarily a triangle?
Yeah, that's a good question. So one thing that's nice about the triangles is that that a triangle can be described just by two parameters. So it kind of lends itself really well to the computer screen. If you wanted to do this for quadrilaterals, one thing you could do, like someone suggested to me that you might look at quadrilaterals that were inscribed in a circle. And that would actually, again, give you a two-parameter family. So yeah, and actually, it would be a great thing to do. But we haven't tried to do this yet.